Thank you, Samuel, for the opportunity to talk on this conference and present one of my directions of research. I'm having a great time here because before I was thinking that only me trying to find these overlaps, trying to use them to find some observables and so on and so on. And it's a real pleasure to get to know many things here. Thank you. I'm going to present today the research made in collaboration with Alexander Pavlotsky. This is ongoing work. Part of it is finished. There is a paper on Archive where you can find more details. It's about interconnection between dense loop models and 6-vertex model. And we exploit it in order to find exact loop densities. So we're interested in observables. This is my plan. So I'm going to start from the problem. Okay, it's going to be opening. Let me formulate the problem first. The object of research is a dense loop model of n, where n is a parameter. And then you can consider different boundary conditions. So here we're taking an infinite cylinder. You can see the strip first of perimeter L, and Z is the horizontal direction. This is first to take two-dimensional square lattice. Then in every vertex you put one of two local vertex configurations, so that path going through every bulk, and then it turns 90 degrees in every vertex, and that's how you have your configuration. Then you look on the loops. You see how many loops you have, and then you're giving it a weight. First you can select the height of a cylinder fixed, and then you're giving a weight to every configuration n in the power of number of loops. And the question we're going to answer, what's the average density of loops? So we're interested in the exact answer here. The motivation to study this model is to study the percolation at the critical point. I think you all know this idea that when you consider percolation and the density is small, then you observe a lot of small clusters. Then there exists a critical point when big unique clusters appears, and a lot of research is about this behavior near the critical point and at the critical point. The case we have here is the simplest one, the most well-known one is the square lattice with the bone percolation, and of course it's going to be the point of self-duality with the critical density 1/2. Then the idea that we already observed in Joule stock, and very often we see it in spin chains, that the situation depends on the oddness of the parameter, like it is here. For even case, there will be one-to-one correspondence between the configurations of dense loop model and critical percolation. So what you do, you just have your configuration, and then in every second square you put a vertex, and then you connect these vertices only if they do not cross loops. And that's how you have a percolation cluster. So the result is, on the one side you have a dense loop model, on the other side you have a percolation cluster on a rotated lattice. It is rotated 45 degrees. This direction and this is direction. And then the answer about, the question about average density of loops is the question about the number of contractible loops. because with the even case you have contractible, and you can also have non-contractible loops like the one going here. It goes from right to left, and it is winding around the cylinder, right? You can see this one. Yeah. And then, okay, we have two types, and the contractible one we have either inscribed like this one loop, or circumscribed loops like this, going around some percolation cluster. And then because we're considering density 1/2, then the density of clusters and dual clusters will be the same, and thus the density of inscribed loops will be equal to the density of circumscribed loop on a dual lattice, and that's why altogether it is the density of contractible loops on a percolation lattice, and the size of these lattices, if you see, it is 2 times less. So that's why in order to measure the cluster density, you can in order to measure the loop density is the same as measure the density of percolation clusters. Let's compare it with the odd case. Well, for the odd case, situation is different, because once you have an odd number of vertices here, these are the odd number of bulks or sites, then you realize that with your configurations, your paths are somehow pictured, loops somehow pictured, but there is always this path going on a cylinder from down up, because it's always unpaired, right? Because of oddness. And the typical configuration looks like this. And the difference here is that once you have this path, now you don't have non-contractible loops. Never. And the question appears, can we still map it to any version of percolation? If we do the same, you can try to picture this percolation, then you see you have a problem with boundary condition, right? You have vertex here, but there is no vertex here. So with these odd size, you have this problem, but this is solvable. So what you should do, you should say, okay, let's take 2 copies. Why not? Left copy and right, and now the boundary condition is satisfied. So these are exactly the same copies. You place them, and again you realize that the density of loops it is the same as the density of clusters. Again, you can say that there are inscribed clusters and circumscribed, and inscribed here, you see inside the percolation clusters, they becomes circumscribed on a dual lattice. And well, in the limit, they will be the same. And because we have 2 copies, so now we're dividing by 2L. So again, this is the density of percolation clusters. So that's why you can use a dense loop model, think about loops, measure density of loops, but it's also is the study of density of percolation clusters at the critical point. Yes?
Can I ask, in the second copy, it looks like you've swapped where the edges are open or closed between the 2. Is that right?
Yeah. Yes. You're right. You're right. You put the second copy. Yes. And now, in order to preserve the boundary condition, you have to switch. You're right. Yes. You're right. You're right. You have to switch now. Dual. Now the dual lattice, the dual percolation clusters in the right hand side is the real cluster. Right. So on a cylinder, it becomes not just any percolation. It becomes percolation, self-dual percolation, which comes to itself if you rotate by p. If you rotate by p, then it becomes self-dual, right? Like this. Yeah, it's a bit tricky, but it appears useful. You'll see. Okay. So, sorry. Oh yeah. Oh, I switched so many. Okay. So the history. So of course the question it was addressed before, and it is extensively studied. But what is studied? So approximately the number of loops was found first. Then was found exact infinite plane limits, and of course, exact solutions by Baxter were used to find again this infinite plane limit. What we're gonna find is the exact expression for the density, and the contribution will be not only the whole formula itself, but also its asymptotic analysis, because the universality is expected in finite size corrections, and it was predicted by CFT theory that this coefficient is universal, although it depends on the boundary conditions, whether it is a plane, cylinder, or something else. And of course, it also depends on the type of lattice you work with. But anyway, it's really interesting to test this universality here. The other direction, which lies very close, is the connection with the combinatorial problems appear that is the ground state of a Markov chain associated with the dense loop model. When you take n equal 1, then it has a remarkable structure found by Razumov-Stroganov, connected with alternating sign matrices. Once you properly normalize the ground state, then its components are enumerating the number of alternating sign matrices, both in odd and even case. And then this hypothesis was proved by Cantini and Spartiello, and then many other hypotheses were done, and then also proved by De Geer, Justine, Philippe Di Francesco, and many people there. Definitely forgot somebody. Okay, results. So the results, we have the original one is this one. So you can have these density for the odd perimeter of a cylinder, which is given in terms of gamma functions. And we already seen these gamma functions on these meetings when we were talking about Heisenberg spin chains in the Young talk. Yeah, we've seen them as an expression for the largest eigenvalue. And here, well, I think that well, this is not the same, of course, but the idea is the same. When we're gonna find this one, we're gonna study the largest eigenvalue, which is somehow expressed in gamma functions, and then you can have this expression. Before was done the even case was done before, and there you have two formulas both for contractible and non-contractible loops. Well, maybe these formulas are a bit bulky, but you can find the asymptotic analysis, which is a very nice result. So for odd case, if you do this formula, then you take n to infinity, then you have this asymptotic decomposition, and this number is universal. It agrees with the continuous XXZ model, with the Raisen-Pill model, with all continuous analogs of dense loop model. Then you can also compare it with the result for even case, and in this case we have here the same number but with positive value. Well, we got a comment that indeed this is very nice, and you can use this knowledge in order to numerically find the number of loops, because if you take average between odd and even, then these parts cancels out, and it gives you numerically very quickly the exact result. and it's an open question whether this is still true for triangular lattice or for other type of boundary conditions. So in this case, this is so. Okay. And then the solution, these are 3 steps here. The first one was to organize, to exploit the connection between the dense loop model and the 6-Vertex model, where you can perform algebraic better ansatz. So you fix the height of a cylinder, and then you define the free energy. And you find the average density of loops as a derivative of a free energy of parameter n, and then you find it when the weight of a loop is 1, right? Because this is when we have the proper measure. So you take the 6-vertex model, you have 6 weights in general, and in our case we're going to have a symmetric type, but so that's why we have C1 and C2. We've done this, then you can apply algebraic better ansatz. So for 6-vertex model, and this is reasonable because you can organize the mapping between weights. So what you do, you take the weight of a loop model, which was uniform, then you say that this weight of a configuration is equal to the weight over all orientation of loops. The trickiest thing is that you also orient defect, and for defect line you can say, okay, let it weight be 1. And for the loop, once you oriented this, if you oriented it clockwise, then the weight will be Q. And if you oriented it counterclockwise, then you give Q inverse. And the desired point we're interested in is called the stochastic point or combinatorial point. This is the cubic root of unity.
Is this the point where the spin chain is also supersymmetric?
Yes. The XXZ at this point becomes, it has a supersymmetry property. Right. But the same configurations for the cylinder you're going to have if instead of loop configurations, you build it out of local vertex configurations of directed dense loop model. In this case, you have to orient every half loop. So in total, you have 8, and then you put weights. The weights reflect the type of loop connections. So zeta reflects the type of loop connections. So this type, first, second, and where it is more, okay, everywhere you have Z is this type connection, and Q reflects the orientation, the total orientation of vertex. And then what you do, then you sum up over all orientations, which from loops, you put this orientation now on the edges of square lattice. And indeed, it is. These are 6-vertex model configurations. So these are 1-to-1 correspondence. So these go here, and there are 2 configurations which, if you assign directions to the edges, give you the same 6-vertex configuration. That's why the weights you take are these. So that's the path you go. So for configuration here for uniform, you give direction to every path. Then you have the weights of a 6-vertex model. And then you use the results of algebraic better ansatz in order to write down this free energy and take the derivative. What you say? You say I'm going to consider the transfer matrix constructed out of matrices, and then going to analyze the dominant contribution. The dominant contribution here is given by the largest eigenvalue, which okay, this matrix is Markovian when n is equal 1, but it's not very nice. And once when we draw configurations, we realize that the dominant contribution, when you take a limit, comes from the configurations with only one defect line. And it means that once you orient the loops, you're gonna have these configurations corresponding to the block to the part of 6 vertex transfer matrix, which has a block structure with almost half spins up and half spins down. So in the vicinity of this point, the dominant eigenvalue here is going to be double degenerate, and we're going to analyze this one. Okay, I think I've said this one. Well, we can note that the basis you use for the transfer matrix of a dense loop model and 6 vertex model is different. But once you realize that the dominant contribution is given you by the corresponding block, then you can use better ansatz in order to analyze this eigenvalue. The dominant one, they take this one and write it down with the help of R matrix, where you put the weights of the corresponding symmetric 6 vertex model, because in the free energy C1 and C2, these were C1 and C2, but they are coming as a product always. So you consider the corresponding symmetric 6 vertex model, just conjugate by necessary matrix, change the spectral parameter, and there you are. There you are, and here you have transfer matrix constructed over matrices, and once you work with the odd perimeter, that's only this, no twist. In the even case, you need a twist in order to take care about loops winding around the cylinder, and here you don't care. And then the whole machinery is working. You have Young-Baxter equation, of course. Q appears there because I changed parameterization a bit when I defined R matrix, so Q appeared. But this is the classical approach. Then again, transfer matrices commute for the same parameter of delta, which in this case is -1/2. So the Baire equation is indeed the same as for xxz 1/2.
Let me ask you something, maybe it's a silly observation, but I have vague memories that in this case the Q is explicit, no? There is this Stroger on J, it's an hypergeometric function, something like this, because you can solve explicitly TQ, but something doesn't work for you probably?
No, it's working. Yeah, I'm going to solve it. Right.
It's one of the rare cases, if I remember well, in which the solution is very explicit. Actually, because it's we proved it's a solution of the differential equation, which is a miracle.
Right. Only yes. Only in the odd case, you're right. You're right. So what you can solve, I'm going to show what you can solve. So you formulate your beta vector with the help of a decreasing spin operator that we discussed before. Oh, sorry, what I had before. You write down the eigenvalue and the Baire equations, and then you rewrite the Baire equations in terms of T and Q operators, which are polynomials here. So you introduce Q polynomial, and instead of these expressions, you express them in terms of Q, and then you have this TQ polynomial, where the function phi is just 1 minus Q in power L, and by T, inside of T there is lambda, rescaled a bit. And then, yes, so the key thing here is that you can solve it. You can solve it in the stochastic point. This one you solve for TQ. In this case, there is also the other polynomial solution, because there is reverse symmetry. So instead of working with spins up, you can work with spins down. So not only TQ you have, but you can also introduce P polynomial and do the same. So finally you have two polynomial relations which are connected by the Wronskian relations like this. So you can rewrite it like this. And then use this phi in order to express t, which is going to give you lambda. And that's it. Then you express your density this way. And the key here is that, in fact, you can solve this TQ relation. That's why you have nice results. And this is called the Friedkin-Stroganov-Zagier solution. This is also done, I think, for a strip. Yeah, and also for cylinder. You rewrite your TQ relation as a differential equation, as a difference equation like this, where the difference is given by this multiplication, and then you can solve it. By guessing the t of u. You guess that t of u is phi of minus u, and this is the equation you have. Well, if you like symmetric functions, then we know that q is a symmetric function, and although it is written here in terms of gamma, which is a rare case, but in fact this is a Schur polynomial. So if you work a bit, in fact this fq you can present it as a Schur polynomial for some Young diagram. This is also very nice. Yeah, the same you do for fp, and then you use this gamma function in order to conclude and find the density. Yes. Okay, I'm not showing you the last part of calculations. Okay, thank you very much. I'm going to stop here.
Any questions to the speaker? So I will give a traditional question. Could you put open boundaries into your story?
You mean like plane limit?
Some sort
of. You can definitely do it for a stripe, and then you can consider any length of stripe. Yes, I think yes. And you can also do algebraic Bedranzats. Yes, expect yes. This is well, I think it's not done yet, but it should be straightforward. I mean the formula, not the Bedranzats.
Not.
Yeah, it's just computation, right?
Yeah, question.
Yeah, thank you for the nice talk. Very ignorant question. So for XYZ model, you also have some supersymmetric planes.
Right.
Are these also related to some kind of loop models, or?
I don't know about it. I know that it is related with the 8-vertex model. There is an 8-vertex model with the supersymmetry property. Like here it corresponds to delta minus 1/2, and there it is a different relation on A, B, C, D. Yes, I know that it exists. I also know that the eigenvectors have very nice properties. You can prove summation formulas, scalar products. They have exclusive properties. That's right. I have not used it for any observables. I'm interested. If you know, let me know.
Any more questions? If not, let's thank the speaker once again.